Okay, so welcome back, everybody. I guess not everybody's back from spring break yet, or maybe somebody's watching the videos from home. Couple of things. So I hope the exam was not too scary. We made sure that after the grading, at least, the results were not too scary. There will be a recitation that walks you guys through all the exam questions with answers this week. So that'll be the topic of this week's recitation. For, let's say, about 30 to 40% of the questions, the solution was almost on the slides. So it's, yeah. Okay. Okay, so some people did extremely well. I think the highest score was 68 or 69 out of 75, which was very impressive. Well, out of 85. Given the time constraints, this was quite a feat. For some of you, so we've been very gentle on the grades. But for some of you, you should look at your handout of the exam questions, and well, you'll get the graded exams back shortly, probably after the recitation. Look at what you got wrong. In some cases, it's a good idea to make sure you know basic math, because in some cases, the answers were unrelated to the question that was being asked. You should try addressing this. That may be a slightly deeper issue that you want to resolve, because it's not going to do you any not going to help you otherwise. So so look at the exam, and if you have issues with the grading, you can go to the TAs and ask them to regrade it. That's it. There's no guarantee that your score will go up. Your score can go down, right? Okay, so you roll the dice, and somebody will regrade it. Please don't do too much of that, because it just costs a lot of TA's time. So you're basically taking somebody else's time by doing that. And somebody else will have a fresh look at it if you feel that you've been unfairly graded. And, well, it can go either way. Okay. So that's pretty much about the exam. Now, I hope you spent the entire spring break working very hard on your projects, right? Okay. Maybe in Florida. We're now back, and I'm going to do a fair amount of math. We'll have to actually accelerate a little bit relative to before the spring break, because we still have a lot to cover, and I want to make sure we get reasonably feature complete. Okay, so today we're going to start with online optimization and then move on straight away to Gaussian processes. And that's a reasonably smallish topic, so I hope that we have all the kernels and everything wrapped up by the end of the week. Next week will be graphical models, a lot of it. And we'll probably stick with graphical models for at least 2 weeks. Okay, good. So let's look at online learning. So this is the parameter path that a set of parameters takes when you run stochastic gradient descent. So we already encountered one of those stochastic gradient descent algorithms when we looked at the Perceptron algorithm, right? And I guess we all recall that very much from the exam. So basically, you get data, you update your parameters, you get some more data, you update your parameters some more, right? And you keep on doing this until you found a more or less good solution. So in that case here, I mean, you can clearly see that the solution goes all over the place. And actually, those different colors are different choices of learning rate adjustments. And you can clearly see that the blue one isn't doing terribly well, whereas if you squint hard, you'll see that the green one, well, it kind of goes here like so, and then it just zooms in right away. So in other words, the green strategy is clearly preferred. What this picture should teach you, and that's the only thing it should, is that if you screw up learning rates in your stochastic gradient descent algorithm, you can end up with a very, very poor algorithm. Right. Okay, so let's just recall the perceptron. So remember we had ham and spam, and we wanted to classify it, and then what you would do is you would get a couple of possible solutions. And the perceptron algorithm did the following thing. Whenever you made a mistake, it would update the weight vector by the data weighted with the labels, not just updated by the data. So some of the solutions, or some of the, well, quote solutions in the exam where somebody just added all the data up, regardless of the label. That's obviously not a good idea if you want to actually distinguish between different categories. And B was updated accordingly here. And so this algorithm is stochastic gradient descent on the hinge loss, and you can easily see what's going on. So the hinge loss is basically this thing here. I want to make sure that all the data is correctly classified. So here I'm going to write y times f of x. And here's the loss of that. So basically, when y times f of x is greater than 0, there's no gradient, well, as in the gradient vanishes. And whenever, well, this is less than 0, less equal than 0, then there's a gradient of 1. And what we will see is that this effectively amounts to updating our parameters by yi times xi whenever. Okay. So now let's actually do this and look at it in a slightly more general context. So what we have is we have an empirical risk. This is basically our training error subject to, whatever loss function that I might be imposing. And under this loss function, well, what we get is that, well, yi, which is what I'm observing, minus phi of xi dot theta, that's basically my estimate f of x. That this is now, of course, that's my empirical average. And what I can do now is I can just update by taking a small step into the direction of each of those observations one at a time. Okay. Now, does somebody have an idea of when such an algorithm will be particularly horrible and an idea when it might be particularly good? Okay. Any suggestions? So this algorithm is particularly horrible when I have basically a fairly diverse set of observations, where each observation contributes something very distinctive and new. And so in that case, I'm not going to do terribly much better than just looking at all the data at once, getting the full gradient. Basically, if the problem is well conditioned, this and very, very high dimensional, then it might not be much of an improvement over a batch solver, also if my data set is small. However, if I have a lot of data, then what can happen is that, okay, let's say, for instance, we want to recognize cats on YouTube videos, right? Because that's the thing to do with a deep network. No, they also do more meaningful things. But if you want to recognize cats on YouTube videos, I guess we all agree that there are plenty of cats on YouTube videos out there. And what this means is if I have labeled data, I will probably have a lot of labeled videos that are very similar. Because it's basically a cat chasing after some round object, or a cat purring, or a cat running across the keyboard, or, yeah, stuff that cats do. So in other words, there will not be a crazy amount of diversity between that. You might even have people liking a video, downloading it, modifying it slightly, uploading it again. In other words, you may actually have duplicates or near duplicates. So if I have what's called a batch algorithm where, as we saw before, you go and compute a gradient, then maybe you compute a Hessian, then just going over the same observations multiple times just means I have to do multiple units of work on that. So if somebody was particularly mean and actually just replicated the entire data set 10 times and didn't tell me and reshuffled it, then I would just end up doing 10 times the amount of work with no apparent benefit. If I do stochastic gradient descent, on the other hand, each time I see an observation, I'll take a small update step, and assuming that one passed through the essentially unique observations gives me 1 unit of improvement, then going through them 10 times will give me 10 times that improvement. And since a lot of real data happens to be of the form where things are quite similar, stochastic gradient descent is actually very good in the large data setting. So you don't only have that with cats. You also have that, for instance, with click-through rates for ads, because, well, I think none of us here in this room likes My Little Pony ads. I hope nobody does. But there is a demographic of people who do. And learning this, while we're all different and unique like snowflakes, we all are, self-respecting nerds, and we like computer science and a few other things. So we actually have more in our profiles in common than you would think. And so therefore, learning it once will help us throughout, and I don't have to learn for each specific user profile again that none of us likes My Little Pony. So what I'm trying to get at is, whenever you have large amounts of data that is poorly deduplicated, in other words, reality, then SGD is actually a really, really good approach. And it's also a ridiculously simple type of algorithm, at least in its basic form, because what it does is it takes some parameter theta, right? That's what I want to optimize over, this guy. And it takes a single observation. So there's actually a typo here. There should be an L. So this loss, which depends on y and the score. It computes the gradient with regard to theta, so the parameter with regard to which I want to optimize. And it takes a tiny step in that direction. And sometimes, if I don't want my parameters to get too large, then what I do is I go and take this update step, and then I project things back onto whatever geometric object that I might have. So for instance, I might go and project it back onto a ball. So in this case, you get something like that. Let's say this is our ball. And here's my parameter before. And I take an update. Okay, so I end up out here. And then I pick another color that's visible, and I project back onto the ball. Right. And then maybe you take another update step, and then you project back onto the ball. And if I know that the optimal solution has to be constrained within the ball, then I can prove that this projection step will never make things worse. Okay, so those projections can be L2 balls. They could also be L1 balls. So an L1 ball is in 2 dimensions, is that kind of object. Well, here the axis. In 3 dimensions, well, you get the corresponding thing here. Yeah, sorry, drawing with, this is kind of hard, and I guess you get the idea. So projecting back onto a ball sometimes can actually mean that some of the coefficients will be 0, right? So that's actually quite a common thing if you have L1 type of sparsity. So in other words, you have something like the 1 norm of the parameter vector. Then actually what happens is you project back onto the ball, and essentially all the coefficients that are less than some threshold get nuked out. Everything else survives. It's just shrunk. Same thing as wavelet shrinkage. Any questions about that so far? Okay. So this is really just the most basic stochastic gradient descent algorithm. You should remember that. As in, it would be kind of embarrassing if you took this class and didn't remember it. Now, what we're actually going to do is we're going to show that this thing converges. You can get arbitrarily complicated in terms of how advanced and fancy your convergence proof is going to be. I'm going to walk you through the very, very simple case. So this is Nesterov and Viol who have this proof. And yeah, this is probably about as simple and painless as a SGD convergence proof gets. So it's not a worst case analysis for that. For instance, Ratliff, Bagnall, and Sienkiewicz, so they were all at CMU. They did a very good analysis, or Bartlett and Hazan. So the pointers are at the end of the slides. Don't worry. OK, so what I'm interested in is how my expected loss is going to behave relative to the optimal loss. And the expected loss is, well, the loss that I will incur from the parameter theta bar that I'm going to get out of the optimization algorithm. Right? So this is not a regret bound, which goes like, well, throughout the entire process, how will I do? But this is really just looking at the overall loss. OK. And the statement basically goes as follows, that it's bounded by the initial loss plus a sum over, so something that depends on the Lipschitz constant of the gradient, of the loss. So in other words, if my loss function changes very little, then the problem is easy. If it can change a lot, then it's hard. Times the sum over the squares of the learning rates divided by the sum of the learning rates. So what you now want is that basically the denominator needs to grow a lot faster than the numerator. And in that case, I will get that this quantity here goes to 0. Right? So for instance, you might have something like eta t being 1 over square root t. And in that case, basically, the numerator will go like log, and the denominator will go like, square root, and then you get a decent rate. So let's just plug that in for the moment, such that we can see. So eta t is order 1 over square root t. And if I do that, then I know that sum over eta t is order square root t. And I know that sum over eta t squared is order log t. And then I get basically order log t plus a constant divided by order square root t. And so this is basically log t over square root t. This is a very, very coarse analysis, and you can get rid of the logs and so on. So you can make it a lot prettier. But this is just to give you some form of intuition of what kind of results you might be able to get. And the way how we're going to prove it is we're going to show, and this is actually a bit stronger than what we need, that the parameters themselves converge to the minimum, to the optimal parameters. So note that this is stronger because, well, this actually assumes that the parameters themselves are meaningful in some form, which they don't necessarily need to be, but here, under certain reasonably strong assumptions, we can actually do this. So any questions on the basic concept? Because, OK, great.
Is that 1 over, is that the capital T minus 1? So it's the number of total cases you look at,
So capital T is the total number of instances that I look at, yes. And I may decide to go through my data set more than once in random order, right?
But that's what that is. It's a function
Yes.
of how many times.
Yeah, so basically capital T is your counter of how many observations you've seen. So this is about as simple as you can make your algorithm. You know, for I equals 1 to capital T, loop through your data. And this is basically not the loop, this is not the counter for the outer loop, but the total instance counter. So what we're going to do now is we're actually going to, well, look at the proof. So RT, that was the distance between the current set of parameters and the optimal solution, right? So RT plus 1 is, well, we are doing our projection of, well, theta t minus eta t gt. So we're basically moving downhill, minus theta star. We know theta star has to lie within the ball, so therefore this projection can only make things better relative to the unprojected solution. This is an extremely common trick that you use. Right? Any questions?
I didn't get why it must become better.
Okay. Well, let's draw a quick picture. Well, if I know my theta star is inside the ball, and if I'm anywhere outside the ball, then projecting onto it can only, in an L2 sense, so can only reduce the distance between the point and this distance. You can prove that.
It's not an optimal function. It's a distance between parameters.
So I'm looking at the distance between the parameter and the optimal parameter, right? So I'm not concerned at this point about the loss function itself. So I said this is proving something that is stronger than what would be needed. Okay. And so projecting inside a convex hull, inside a convex set, will only reduce the distance between the point outside the convex set and a point inside. Okay.
Stronger compared to what?
What's stronger? Well, the distance is shorter.
You said
Sorry, I'm having trouble hearing you here in front. I'm fairly sure everybody else. Do you mind please speaking up, because otherwise the guys in the back can't hear what. I mean, you're asking very good questions, but please let them also hear it.
okay. So you were talking about like we are proving something stronger than we needed.
Correct.
Stronger compared to what?
So the statement that we are proving is that our parameter estimates are convergent. All we really would care for the purpose of minimizing the risk is that the parameters that I'm going to get will be close, will lead to a loss that is close to the optimal loss. So for instance, imagine that I have a couple of parameters where the solution really doesn't depend very much on it. Then for those parameters, I don't really care very much about what the actual values are. And so in this case, I may get a very rapid rate of convergence in terms of my loss, but not a very rapid rate of convergence in terms of the parameters. So for instance, imagine that you could explain the sunrise and sunset by assuming that there's a horse cart drawing the sun across the sky. This is what the Greeks believed. And you can also, understand how, the planets move and therefore do it. Now, these are two very different parameterizations in terms of how you understand the universe, right? But both will come up with identical predictions of what's going to happen the next morning. So your loss function, if you just care about sunrise and sunset, will be identical under those two very different parameterizations. And I think we can all agree that one parameterization is correct and the other one, is fantasy. And effectively the same thing is what can happen in optimization. So you only care about the regret. You only care about, well, basically, for instance, distinguishing apples from oranges really well. Whether I distinguish apples from oranges because, well, one looks like an apple or an orange to a human for all the reasons that they are, I don't really care if I just care about, risk minimization. Because it might just be that the entire batch of apples were rotten apples and they had worms in it, and the oranges didn't. And so if I can detect, wormholes from round things without wormholes, this may be perfectly sufficient, right? So that's essentially why there's a difference between conversions in the risk and conversions in the parameters. Okay, good. Now, back to this. So we go and project. We project onto the convex set, and not projecting can only make things worse. So it's an upper bound. Well, the reason is simply, if you think about it, this projection applied to theta star will just leave theta star equal to theta star. And it so happens that, well, the distance between projections and the distance between the original objects, well, the latter bounds the former. Right? So, in other words, I could sneak a pi x in here, and it wouldn't change things, right? Okay, good. So now, expanding terms, and this is also a common thing to do, well, what we get is we get this gradient squared, and we get 2 eta t of theta t minus theta star gt. Okay. Now, here's the next thing that we can do. So first of all, this gradient itself is upper bounded by the Lipschitz constant, right? So we can just upper bound it by L squared. And now we need to actually do something useful about this last quantity here. Now, if you think about it, since we have convexity, this is basically, well, we know that the gradient at t equals, well, at theta star vanishes, right? Because that's the optimal gradient. And so what I can do is, I can, well, since I'm looking at the expectation here, I need to compute the expectation of this block. And what I can do is, I can therefore argue that this is equal than the optimal value minus the expected value. This is basically the Taylor expansion, right? Because we know that the first order Taylor expansion gives us an upper bound, in this case, on this term here, and so that's what we get. So that's why this inequality holds. Okay, let's work through it in algebra. Okay. Document camera. Okay. Okay, so we know that, well, okay, so this is basically nothing else than theta star minus theta t dot gt, right? So all I've done is I've just flipped the signs here, right? And I'm pulling out the 2 eta t up front because, well, we're not really touching it, right? So what I need to show is that this is less equal than L star minus L of theta t. Okay. So we know by convexity that, well, remember this is a convex function. And here is, let's say here's theta star, here's theta t. And I can just compute the gradient here. So I know that L of theta star is greater or equal than, sorry, that's theta t. L of theta t times, well, plus, and now here we have theta star minus theta t dot inner product d theta t of L of theta t. That's just the Taylor expansion, right? So this is basic convexity. And now, if you look at this, that's exactly what we have up here, right? Because that just happens to be theta star minus theta t dot gt. Remember, that's gt. And so therefore, it follows that 2 eta t theta star minus theta t gt are, well, less equal than 2 eta t, and here we have L star minus L of theta t. And now, if I take the expectation over theta t, because basically, remember what happens is, to update from theta t to theta t plus 1, I draw a random pair of x and y's from my distribution, from an empirical set of observations. So therefore, the change from theta t to theta t plus 1, so basically, that gradient is, that choice is independent. So therefore, by convexity, we know that the expectation can only give us an upper bound. And so, therefore, in expectation, so this is less equal than 2 eta t L star minus expectation of L of theta bar. Okay.
You're off page.
Yeah, thank you. Okay, so we used convexity twice. That's actually the key trick. And then all you do is you just go and, sum over terms, and you're done. So this is so now all I have to do is just sum over all the iterations, and then you get exactly these factors here up front, right? And that's what gives you the optimal solution. So now there's a couple of things that you can do. If we know R, L, and T, then we could, for instance, go and pick a constant learning rate, right? So we just go and pick, 1 over square root number of iterations as the learning trick. If we don't know T, then you can actually go and pick a learning rate that keeps on decreasing. This is actually what you should do in practice. And then you pay an extra log term, but it's not a big deal. And there's actually analysis that lets you get rid of this. And furthermore, if you have strong convexity, and I'm not going to go through the proof in detail, but it's all on the slides, then you can make slightly faster progress, because you can basically in that inequality that we used before, you effectively get one extra term that helps you. So in pictures, strong convexity, just to and that's really all you need to remember. Something with the display is weird today. It displays properly here, but nowhere else. Basically, what happens is, if this is our bound that we get by convexity, right? Okay. Well, I'm not drawing very well today. Then strong convexity means that you can sandwich a parabola in between here. Okay, let's actually do that at 0, then it's easier to see. So let's say we have some convex function here. And what you can do is you can sandwich in a parabola that separates the straight line from my function. So if this is f of x, this is a linear function, x dot theta. And then here I have basically that term plus, lambda over 2x squared.
So the action is like more than 0 positive.
Exactly. That's perfect. So the comment was that it gives me a lower bound on the smallest eigenvalue of the second derivative. And effectively, if you think about it, this is very close to something like a condition number that you might recall from numerical linear algebra. So the condition number, okay, who's heard of the condition number before? Okay, cool. So it's maybe 1/5 or 1/6 of the class. So when you're trying to solve a linear system of equations, as in matrix times vector equals another vector, then one of the important quantities that tell you how hard this problem is to solve is the ratio between the largest and the smallest eigenvalue. And if that gap is really large, then the problem becomes really difficult because you basically have potentially that very small changes can have a big effect relative to the overall outcome. And if that gap is very small, then, well, you know that the problem is easy. What is the smallest value of a condition number that you can get? Yes?
1.
1. Exactly. Perfect. So 1 is the condition number that you can get if the smallest and the largest eigenvalue are the same. In other words, if this is a multiple of the identity matrix. In which case, solving the linear system of equations is trivial. Right? It doesn't have to be the identity matrix. It could be 42 times the identity matrix. But it's a way simpler problem. Right? So the dynamic range is small. And strong convexity tells me that the smallest eigenvalue is reasonably large. Now, upper bounding the largest eigenvalue is actually not that hard if you have a Lipschitz constant, right? Because then you can also work out basically how much things can change at most. And so it actually turns out that the condition number gets replaced by a ratio between the smallest eigenvalue, well, between that condition number and the Lipschitz part. Okay, so let's actually look at that. VGA. So first of all, we can actually, in that case, make faster progress because we can actually go and pick a learning rate that goes like 1 over number of iterations as opposed to 1 over square root number of iterations. And what we'll also see is that now we basically get a guarantee that goes like L squared over lambda. So L squared is basically the equivalent of the largest eigenvalue in the Hessian. and lambda is the smallest eigenvalue. So this is basically just like a condition number, and then it's 1 over number of steps. One of the problems, though, is that, well, if you don't know this condition, if you don't know the strong convexity terribly well, then this algorithm may not actually work quite as amazingly as advertised. So the 1 over square root t learning rate is preferable.
So I have a question. What if you have like the problem? I mean, the loss function does not satisfy strong convexity, and you still use 1 over t. Like, what would happen?
Okay. So very good question. So the question was, what on earth would happen if we actually went and picked a overly aggressive learning rate, even though the problem didn't have all the nice properties required for the learning rate? Well, if you think about it, the sum of, basically, the algorithm will just not converge. It'll stall out at the suboptimal value. And you might not even know what's going on. But you could easily then work out and look at the gradient, and you would see that the expected gradient is not vanishing. Right? So that's also often something that you can use to debug things by just looking at the aggregate gradient over a couple of steps. And if that gradient does not decrease, then you may have a problem. Right? It will not vanish. As a matter of fact, the magnitude of that is what's called will give you what's called a Fisher information matrix, so that covariance, and that tells you basically how reliably you can estimate your parameters. But overall, that's pretty much what you want. So this slide is left intentionally blank for me to draw exactly strong convexity, but I showed it to you before already anyway. But just to do it again, if this is my function, I basically have to be able to sandwich in something right there. Okay. You can do that with different norms rather than L2, but L2 is kind of the most popular one. Now there's a lot more fun stuff that you can do. Namely, you can ask about adversarial guarantees. And I'll just tell you what they are, as opposed to going into the algebra in a lot of detail. Basically, you can actually connect a lot of this online learning to game theory. Who's done game theory before? No hands goes up. Well, one. Great. So essentially, you could think of this as being a game that's being played between me, who needs to estimate the parameters, and an adversary. And the adversary is allowed to give me observations in any arbitrary order. And my task is to come up with some parameters, and I can change those over time. And essentially, my task is to find an optimal set of find a sequence of parameters in such a way that the loss that's incurred is no much worse than the best loss in hindsight. In other words, you ask me a question, I give you an answer. You ask me a question, I give you an answer, as in I make a prediction. And I can change my mind over time in terms of the explanations. And the point is that I should not be much worse than one set of explanations that remains unchanged over the entire set that's chosen in hindsight. Okay, that sounds maybe a little bit complicated. Let me give you an example where this is actually not the best thing you could possibly do. Imagine that I have a situation where the adversary first gives me 100 zeros and then he gives me 100 ones, right? And let's assume that my loss is a least mean squares loss. If I'm somehow smart enough to figure out that it's going to be 100 zeros first and 100 ones second, then, well, I can get a loss that's pretty close to 0 because I will pretty accurately, have almost all zeros and almost all ones. So, on the other hand, if I need to come up with one consensus answer throughout, the best thing I can do is I can use 1/2, and so then my loss will be 1/2 minus 0 squared or whatever, and 1/2 minus 1 squared. So that's where being forced to have one common explanation can actually do worse than being allowed to change your mind. But the guarantees that you get are usually of the form, well, that you're not going to do much worse than the one common solution throughout. If you like this kind of work, you should look at the Ratliff, Bagnall, and Sienkiewicz paper, and then Shalev, Schwartz, and Srebro and Singer. They basically got the faster learning rate under, well, basically certain additional constraints, which are actually more or less the same thing as strong convexity. And one of the nice analyses is probably the one by Bartlett, Racklin, and Hazan. This is NIPS, I think, from about 5-6 years ago. Okay. Any questions so far about SGD? Okay. So for the parallel and distributed versions, I will not go into a lot of detail. You can look this stuff up on the slides. What I'm just going to do is I'm going to explain a little bit the two different strategies that you can use. And they've now come under colorful names. And I think adding this name was probably one of the major contributions there. Who has heard of Hogwild? Okay, this is the name of an algorithm. And the algorithm basically goes as follows. If you have an optimization problem, well, just go and... Okay, so let me explain the problem. The issue is, well, your desktop computer by now may have 16 or 32 threads. Well, 16 threads if you use a single core i7 highest end, 32 if you use something a little bit fancier. Your desktop works, your servers may actually have 64 threads or more. If you go to Amazon, you can get on a spot instance 64 cores for, I don't know, 10 cents an hour. So it's very affordable for everybody to use that kind of stuff. Now the problem is, what we just saw with our online learning algorithm, stochastic gradient descent, it basically took one observation at a time, did an update. So if I have 64 cores, or at least 64 threads, then that means 63 of them are going to sit idle. You could, of course, say, well, we can always use numerical linear algebra and compute inner products in parallel, but that's pretty weak. In particular, it's pretty weak if you have many computers. So the question is, how can I actually make use of many resources at the same time without them having to synchronize and coordinate very tightly? What I can do is I can basically give each of my processing units a subset of the data. So that's this here. We saw that in MapReduce, right? In MapReduce, basically each mapper gets a fraction of the data. They then go and compute some loss gradient, each of them individually. And then they go and update my parameters accordingly. And essentially, some of the papers went around whether you should lock or not lock and how much you're going to lose if you lock. And usually asynchronous and lock-free are the things that you want, because that just means that all the machines can hammer the problem at as fast a rate as possible. And by now there are a couple of papers that do this, so you want to look for Hogwild. Okay. So we had a precursor to that called Slow Learners Are Fast, where it looks at different constraints, and I'll get to the parts of the proof. But basically, the Hogwild paper is probably the key reference that you want to look at. Now, another thing that you can do, especially if each instance is really huge, is you can actually have your data. Let's say I have a huge parameter vector. And I can now have each machine process parts of that. This keeps on getting reinvented and usually implemented in an appalling fashion. Sufficiently appalling that sometimes then 10 to 100 to 1,000 machines get about the throughput of a single machine. And then they prove very nice scalability in that. I've seen it in at least half a dozen papers, some of them by supposedly, good places. Do this only as a last resort if your problem is so big that it does not fit entirely into your machine in some form. Because what now happens is that you will actually need to synchronize between machines for each observation of which you're going to have a lot, the partial solutions. This is very expensive. So if I have, let's say, 10 to the 10 observations, which is not an uncommon problem. So 10 billion is basically what Facebook's users generate probably in a day. Right? So this is not an unusual thing. Now, if I have 10 billion observations and I perform this partitioning over maybe 100 machines, that means that I will immediately have to deal with 10 to the 12 parameters that need to be synchronized and kept in sync and exchanged and communicated between machines. And that basically just means that I am going to, if I use something like floats, I need to generate 4 terabytes of network traffic just to exchange this. Right? So be careful before you do this. Use it as a last resort if nothing else works, because the price is very high. This is probably about all I want to tell you about the conceptual issues there. Yeah, but there aren't like a crazy number of different strategies how you can distribute a problem. These are sort of the main ideas there. Okay. Any questions so far? Okay, now we are going to we're going to skip through a whole bunch of stuff. And yep, so there's all the guarantees. What I will quickly go through is a little bit of discrete optimization. And that's just because it's almost never taught in meaningful detail before, and there are some cases where you will encounter discrete optimization, and you should not just throw Cplex at it because you don't know any better, right? So in many cases, problems can actually be turned into something meaningful. Okay, so the first thing is you might have something called an integer program, an integer linear program. So an integer linear program is just like a linear program. So I want to, let's say, minimize C transpose X. Under some constraints, AX less equal than B. But I have this pesky additional constraint that X has to be integral. Now, there are a couple of ways how you can solve this. One is you could just go and say, well, I'm going to ignore the fact that X has to be integral, and I'm going to solve the problem. So you'll get something out of it, and it's not integral. And then what you could do is you could just either pray and hope, or you could make things integral. And if you make things integral, then something very horrible is going to happen here. But that can actually be worked around. So the fact that something horrible might happen here, you can sometimes deal with by just imposing a slightly stricter constraint. So maybe AX less equal than B minus epsilon. And then you're not going to get quite such an optimal solution. Sorry, it reads like a Z here. Okay, so let's make it Z. But basically, then randomized rounding, especially if you have a lot of variables and you don't have too many constraints, you may actually be able to show that with high probability you're going to find an integral solution that actually satisfies the constraints, where with randomized rounding, this term here isn't too bad. So for instance, if you have 1 billion web pages, this is a really good idea for optimizing caching layout. And so that's, for instance, one of the things that we actually did. Because it doesn't really matter that much where a specific web page goes, but it just matters that in aggregate you're not going to exceed the number of pages in any specific cache by too much. Quick question, does somebody know how web page caching and so on actually works on a search engine? Probably not so much. So basically what happens is, by now, search engines probably index something. Well, I guess it's not an unsafe bet to assume that it's probably in the order of 100 billion web pages. And nobody will tell you anymore exactly how many it is. And since a lot of content is dynamically generated, asking that question is kind of pointless anyway. You can actually download about 10 billion of that as part of the Amazon Common Crawl. Well, no, don't download it from Amazon because you'll go broke. Send them a disk, have them copy it on the disk and ship it back. That's a lot cheaper. Yeah. But what happens is that if you return those search results and you need to get annotations, snippets, and whatever for that, you want to distribute you basically want to keep the most commonly retrieved results in a cache that has maybe higher availability, is more often replicated and all that. And so what you end up doing is you end up having to tier the results based on their popularity. And unfortunately, you have this additional pesky constraint that when you return search results, you need to wait until the last of, let's say, if I return 10 results, until the last of those 10 results has been retrieved. So therefore, not only do you care that the popular results are there, but also that the pages that show up commonly with popular results are also in the same cache. So that's why it's not just a frequency ordering problem. You can actually turn that into an integer program and then solve it directly through that. But that's an example of where you actually get at such problems at a very large scale. Those things have interesting, colorful names like WOW, as in worst of web, which is then the really infrequent set of pages that you might look at, or landfill, depending on basically whoever designed the system. Likewise, Google Instant essentially caches the search results pretty much. So as you type in your query, it just looks at the full result set directly. Okay. Now, one nice thing is that there are some problems where actually the constraint set is such that the vertices of the constraint set are all integral. And this is called totally unimodular. And what you should do is, if you ever encounter an integer programming problem in your life, is the first thing you should do is you should actually look at, is my problem totally unimodular? And if it is, then you're in luck, because you can just look up the solution. You can basically just ignore the fact that it's an integer programming problem and solve it. And we know that the optimal solution for a linear program must contain a vertex. And so therefore we're done. So let me quickly graphically prove to you that the optimal solution must contain a vertex. So if my objective function is C transposed X, then let's say this is C. Then you can clearly see that as you move along a facet here, you will want to move in this direction until you hit the vertex. And now if I had, for instance, something a little bit more sneaky, such as a objective function that was at right angles, then yes, anything on this line here would be an optimal solution. However, it means that I can move on that simplex given to me by the set of optimal solutions and find a vertex, let's say this one here, or that one there, and I'm done. So it does not guarantee that if you run your LP solver, you will get an integral answer. It'll just guarantee you that an integral answer can be found among the set of your solutions. And so what you may have to do in the end is to walk on that simplex and find a vertex. But that's a lot easier than solving the problem otherwise. In some cases, though, this can lead to a problem that's both totally unimodular and NP-hard. So parametric flow problems are something of that form. Okay. Here's a nice application, namely Hungarian marriage, or just, the matching a marriage algorithm. So the story basically goes as follows. You have N Hungarian men, N Hungarian women. They all pairwise like each other more or less, with some compatibility Cij. And the Cij is particularly large if they like each other a lot, and it's less large otherwise. And so what we want to do is we want to find an optimal matching. And this optimal matching is basically that everybody must get married. They have no choice. Furthermore, if somebody would rather like to be off with somebody else, they need to swap partners. So you cannot just say, well, hey, I would like somebody else, but then if they don't like your partner, then, okay, you cannot perform this swap. So this is math, not life. So what you basically end up doing is you end up optimizing over the set of permutations. So this matrix pi is basically a matching matrix. So it has, let's say, an entry here, an entry there, an entry there. And this just means that 1 pairs off with 2, 2 pairs off with 1, and 3 pairs off with 3. Okay. So those are the 3 pairs. 1, 2, 2, 1, 3, 3. And that's just written out here in math. Basically, the entries of this matrix pi have to be zeros or ones. That's a 1, all the rest are zeros. The sum over the rows, or the sum over the columns, have to be 1. And I want to find an assignment here. And it just turns out that this is, while it's an intimidating integer programming problem, it's actually totally unimodular. So there's a simple set of constraints that you can check, and you should just go and search that on Wikipedia when you encounter that problem. Don't bother very much about it now, but it just means that this is actually a linear program. And you can find the optimal solution this way. Here's another thing that you can use if you want to do optimization efficiently. This is a very effective algorithm if you want to maximize things and you don't care about the perfectly optimal solution. Let's say I want to find the maximum over a very large set of instances. And maybe I don't quite care about the maximum, but just about the approximate maximum. So things like that are quite useful in the context of load balancing, where maybe I don't necessarily want to send this to the machine with the least amount of load, but at least to a machine that has fairly little load relative to anybody else. Because rather maximum you can have minimum too, right? And so a simple strategy is just you go and draw a random subset of n terms. And then you take the maximum of the subset. And the really useful rule of thumb is this 59-95 trick, which is basically draw 59 observations at random. And then with 95% confidence, you'll get something in the 95% quantile. 59 samples out of maybe infinitely many samples. It doesn't matter. what the original bag was. That's the nice thing, that you now have something that's very easily treatable, namely 59 instances, and you'll still be fine. So for instance, if you want to buy a house, right, and there's maybe an infinite number of houses in Pittsburgh that you could possibly buy, you go and only check a, maybe not entirely random subset of 59 houses, and you call it a day, and you just pick the best one out of those rather than keeping on searching forever. So the reason why this works is basically just a cumulative distribution function. So if I have some random variable xi, and I have some CDF f of x that goes with it, then the max over I equals 1 to n of xi, and let's just define this to be Zn. Then Zn has a CDF that is given by f of Zn, basically the same CDF raised to the power n. Because basically, for something to be greater than z, it has to be greater than all the xi's in that sum, in that max. And so therefore, I have to multiply the probabilities that it's greater than the first term times it's greater than the second time up to the nth term. So this is exactly why I get this raised to the n. Now, if I have a uniform distribution, then something to be in the epsilon quantile has a probability of 1 minus epsilon. So in the 1 minus epsilon quantile. Now, if I have n of those terms, I get exactly that raised to the power n. And now, if I want to make sure that this holds with confidence, delta, then all I have to do now is I just plug in epsilon being 0.05, delta being 0.95, and by just working out the numbers, I get something like 58.55 or whatever, so 59 are definitely enough. Okay. So this is a reasonably useful trick that you might need occasionally. Now, there's a lot more that you can do in the context of randomized algorithms. So usually what you do is, in order to find a good solution, well, you show, okay, did you have a question?
Does that previous slide require uniform distribution?
No. So actually, very good question. So this works for any distribution in order to get into the quantile. Now, however, if you have a very heavy-tailed distribution, then in absolute terms, the solution may not be particularly good. So let's say, for instance, you're searching for Mrs. Right, right? Because you think that there's this one soulmate in the world, right? So then you have this insanely heavy-tailed, well, basically, there's only one person in the entire set, who's right, and nobody else will fit the bill. And unless you actually exhaustively search that set, you will not find her, right? So this is an example where this random sampling strategy will not work. On the other hand, if you think that, well, maybe the distribution isn't that heavy-tailed, then, well, okay, maybe 59 is slightly excessive, but I guess you get the point. Yes. So this is an example where, if you have a very heavy-tailed distribution, the solution that you get by randomization may still not be so great. Okay. Now, overall, randomization is a really useful strategy. There are a couple of really nice books. If you like this kind of analysis, you should look at them. They're both brilliant, both by Raghavan and the late Motwani, randomized algorithms, and then, if you like something slightly more mathematical, by Lon and Spencer. And most of the analysis goes as follows. Pick a randomized algorithm, show that it behaves well in expectation, and then show that the expected case is not terribly abnormal. Right? So we actually did this for convergence analysis, right? We basically looked at cases where in expectation things were good, and then we showed concentration for that. And likewise, finding a good majority, and you just go and show that the majority satisfies a nice condition, and if not, then you basically show that it's very unlikely that the minority gets overrepresented. So this is, for instance, if you want to compute medians, you want to make sure that the really small guys or the really large guys will not, by some stroke of really bad luck, overrepresent the set of solutions that you get. So this is at the conceptual level, but it's actually something that you're going to encounter quite a lot if you design your own algorithms. And I can only really recommend you the Raghav and Motwani book. It's great. Last, I quickly want to go through submodularity. So a submodular function, by the way, who's heard of submodularity? Okay, awesome. So actually, let me motivate it in a very simple case. So imagine, well, when you were maybe in elementary school and your parents gave you $1 or, 1 yuan or whatever currency unit raise in, your pocket money. That was a big deal. Getting $1 more, you probably cared about it. By now, you care a lot less about $1 because you get more than that as your stipend. And once you have a real job, you'll care about it even less, right? Then, if your boss comes to you and tells you, well, you should be happy you're getting a $1 pay rise, you will probably think that your boss is either really evil or, yeah, you should probably change jobs. So, in other words, what's happened here is that incremental value of $1 has decreased drastically as a function of the amount of money that you're already earning. So you basically have diminishing returns, a diminishing gains property based on what you already have. Now, or likewise, if you are very poor, then maybe, getting one extra dress or whatever makes you very happy. But if you already have a lot of different clothes, then that one extra dress will make you less extra happy. And it depends also not just on how many dresses you have, but also on how different that dress is relative to what you already have in your wardrobe. So in other words, what you get is a function that has a diminishing returns property and where the diversity relative to what you already have in your set matters. Okay, so in math, here's the condition. It basically says that the increment that I'm getting from adding C to set A, so these are functions defined on sets, and basically the increment that I have is the set C. That the increment that I'm getting by adding C to the set is larger than adding C to set B, provided that A is smaller than B. Right? That's essentially the condition. So, for instance, for web search, this is exactly that diversity versus relevance trade-off. If you might have a total ordering on search result quality, and this person clearly likes chocolate over anything else, but he may not only want to get chocolates. So, and we'll actually formalize that and look at an optimization problem and how to explicitly express that with new search. We'll do that in the recommendation part. But this clearly shows that you should actually value diversity over just only picking relevance ordering, because the happiness of the user is submodular. Yes?
So, do you also need monotonicity in RF?
So what you have is that individually, those items may have a total order, but what will happen is that the information gain that you get by adding, let's say, an apple is higher than adding another piece of chocolate. So for instance, examples are set cover, examples are entropy. So in all of those cases, so basically having extra observations is good, but it helps you less the more observations you already have. So that's basically an example of a submodular function, and people have actually used that and gotten best papers out of that maybe about a decade ago by modeling such problems as submodular. By now, submodularity in machine learning has taken off quite seriously. So there are basically Andreas Krause, Steffi Jegelka, Jeff Bilms. These would be probably the key people in that context. Look at their work and you'll see a lot of nice applications of submodularity. Okay? Does that answer your question? Or?
I was originally asking if that condition is enough to show that for a larger set like set, say FA is lesser than equal to FB.
Mm-hmm.
Is it enough?
Okay, so the question was, if I understand it correctly, that if I just show that FA is less equal than FB, then this would be enough. No, it's not.
I mean the other one. The other side.
Okay, maybe we can take that offline because so the reason why just looking at the function values here does not happen to be sufficient is because what you might care about is how different A and how that you could have sets A and B that are quite different. So, for instance, assume that let's look at a practical example. Let's say my happiness depends on how much food I have and how much money I have, and let's say set A is only about food and set B is only about money. Then, if set C is only about food, then food plus food doesn't make me that much extra happy, but food and money will make me a lot more happy, right? So this is an example. Okay. But given that I have a couple of people already outside, and given that I quickly want to tell you the algorithm, let me tell you the algorithm on how to optimize it because it's ridiculously simple. It's a greedy algorithm where you basically just add one element to the set at a time. And that turns out to be near optimal. So basically, you just pick the next best element to add. And the guarantee is that this will give you an approximation that is within 1 minus 1 over E. Good. And this is basically the submodular greedy optimization algorithm. So this is the one thing that you want to remember out of submodularity. Okay. You can use it for a lot of stuff, and we're really out of time for today. On Wednesday, we'll do Gaussian processes. Okay. Thank you for your time. You press. Yes, sorry I had to cut you off, but basically.